Welcome to the Explainer. We hear so much hype about massive machine learning algorithms, right? But today, we're zeroing in on the fundamental gap we have to cross before any of that magic happens, translating our messy, complex real world into a format that a machine can actually process.
So how do these algorithms actually ingest all our messy, chaotic, real-world data? I mean, you can't just take millions of raw app logs or clunky customer records and dump them straight into a model, expecting brilliant predictions. It just doesn't work like that. The machine requires a strict mathematical vocabulary.
Okay, let's dive into this. The bridge between our human context and the machine's mathematical world is called feature engineering. It's this intensely labor-intensive but highly creative process of transforming raw data into a clean data set of mathematical vectors. Honestly, it's the secret sauce of machine learning. It's where human intuition and domain knowledge are absolutely crucial to building a predictive model that actually works.
Here is the Data Analyst Toolkit, which will be our roadmap today. We'll start with Section 1, what is feature engineering? Then Section 2, One-Hot Encoding Categorical Data. Section 3, Binning continuous features. Section 4 covers normalization and standardization. And finally, Section 5, dealing with missing data.
All right, kicking things off with Section 1, what is feature engineering?
Before we pull out the specific tools, think of it like prepping ingredients in a kitchen. The algorithm, that's your high-tech oven. Sure, it's incredibly powerful, but your raw data is basically an unpeeled whole onion. You definitely can't just toss it in whole and expect a gourmet meal to pop out. Just like in a busy kitchen, every measurable event has to be chopped, diced, and marinated into an informative feature before the algorithm can actually digest it.
Moving right along to Section 2, One-Hot Encoding Categorical Data. Now, what's really interesting here is the stark contrast between how we see categories and how a machine sees them. To us humans, a category is just a descriptive word, right? Like red, yellow, or green. But to a machine, red becomes mathematical vector bracket 1, 0, 0. Yellow becomes 0, 1, 0. And green becomes 0, 0, 1. So what we've done here is literally transform a single categorical feature into 3 separate, independent binary features. You might be wondering, why go through all that trouble with brackets and zeros? Why not just assign simpler numbers, like red is 1, yellow is 2, green is 3? Well, actually scratch that, because using ordered numbers for categories implies a completely fake mathematical hierarchy. It essentially tricks the algorithm into thinking that yellow is somehow greater than red, or that if you average red and green, you get yellow. It forces the machine to find patterns where there literally aren't any, which is a one-way ticket to overfitting. By expanding the colors into independent binary dimensions, we completely avoid that trap.
Next up is Section 3, Binning continuous features.
Interestingly, this is the exact opposite of what we just did. Now we're taking a continuous numerical feature and turning it into a categorical one. First, you take a continuous feature, let's say an exact age, like 13. Next, you chop that entire age range into discrete logical buckets, say 0 to 5, 6 to 10, and 11 to 15. Finally, we assign our specific age to the correct binary bucket. Since 13 falls squarely into our third bucket, age bin 3 becomes 1 and the others are set to 0. Just like that, we've successfully translated a wild, highly variable number into distinct, manageable categories.
So the crucial question here is, why on earth would we intentionally strip away exact mathematical details? Well, binning gives the learning algorithm a massive hint that the exact value doesn't really matter within a specific range. Think about it. Whether a user is exactly 12 or 13 probably doesn't matter at all for predicting their movie preferences. But knowing they generally fall into the 11 to 15 demographic, that's highly predictive. It's a brilliant shortcut that dramatically simplifies the data processing, allowing the algorithm to learn using far fewer examples. Okay, let's move to Section 4, Normalization and Standardization.
The formulas used for this brilliantly illustrate the heavy lifting going on under the hood to squeeze and rescale natural numerical ranges into standard mathematical formats. The underlying algebra here is pretty elegant, but more importantly, it's absolutely necessary. Because if we don't tame these wild numerical features, computers will seriously struggle with extreme numbers. We're talking straight-up hardware-level numerical overflow, which we definitely want to avoid.
Let's contrast these two methods really quickly. Normalization effectively squeezes actual ranges. Imagine house prices ranging from $100,000 to $1 million into a standard, tiny interval.
typically between 0 and 1 or -1 and 1. Standardization, on the other hand, completely rescales the data into a standard normal distribution, or z-score, which centers the average right at 0. As a general rule of thumb, standardization is highly preferred for unsupervised learning, especially when you're handling extreme outliers or bell curve data. Meanwhile, normalization works beautifully when you just need to keep standard inputs safely within a small mathematical range.
Finally, we arrive at Section 5, dealing with missing data.
This final set of tools addresses the universal headache of data analysts literally everywhere: the dreaded blank cell, the corrupted log, or the forgotten measurement. It happens. Thankfully, analysts have a vast breadth of imputation techniques to fix these holes. You could just remove the incomplete examples entirely. Or you can intelligently replace the gap with the dataset's average value for that specific feature. Sometimes, you might use a value totally outside the normal range, like -1, just to firmly flag to the machine, hey, this is weird. You could use a neutral 0, or, and this is pretty beautiful, you can actually build a completely separate regression model just to predict what that missing value should have been. Lastly, you can always just add a new binary indicator feature that explicitly flags the missing data to the algorithm right from the start.
Wow, we have covered a tremendous amount of ground today, looking at how data analysts meticulously chop, encode, bin, scale, and patch up raw data into absolute mathematical perfection. But this whole process leads me to a final, kind of provocative thought. If humans are the ones making all these highly subjective, deeply creative choices about exactly how to translate the real world into math, then how much of machine learning is actually human? Think about it. Behind every single sophisticated algorithm is a human being, meticulously curating the exact version of reality that the machine is allowed to see. It's wild. Thanks so much for joining me on this explainer, and as always, keep questioning the human data behind the machine's algorithms.